There's lots of genetic defect in everyone. We think the average healthy person has a couple of hundred genes with defective function in their genome. And there's probably lots of what we think of as subclinical symptoms wandering around across the whole population. So I think that's kind of the future vision of the company is everyone would benefit from having a full understanding of their genetic background. And it's a complicated problem that the doctors don't understand. The patients certainly don't understand. And they were really at the frontier of understanding.
You're listening to Gradient Descent, a show about machine learning in the real world, and I'm your host, Lucas Bewald. Matthew Davis is the head of AI at Invitae, a medical genetic testing company. He applies a really wide range of machine learning techniques to the genetic testing problem, which I think is one of the most interesting applications of ML today. I'm super excited to talk to him. Invitae is actually a household name in my house because my wife runs a startup that sells to Invitae, and I run a startup that also sells to Invitae. So you're one of the very few overlapping customers to us. So I feel like I know Invitae very well, but I was thinking if that wasn't the case, I would definitely not know Invitae. So I was wondering if you could describe kind of what Invitae does and how I might interact with your products as a consumer.
Yeah, sure. So for starters, we're a medical genetic diagnostics company. And I'm pretty sure by volume of test, we're the biggest in the world.
Which is amazing because you're fairly new for a public company, right? Didn't you start in 2010 or something like that?
Yeah, that's about right. So the company itself is about a decade old. And it's not a coincidence because the availability of high throughput, low cost genome sequencing really came online in like 2008 with Illumina, like making a scalable platform. And at that point, it became clear that instead of analyzing one or two genes at a time, that you could be analyzing lots of genes for less money. And I think the strategy that was clear to the founders was here's a market it's a very narrow market with a very high margin that actually should be an addressable market of everyone with access to modern medicine. And instead, the cost could be low and the volume could be high. Mm-hmm. And that if you pursued that strategy, there was actually way bigger benefits to like mankind and also shareholders of a company because you'd start to learn things about medical genetics and disease and probably most importantly, relationships to treatments that you weren't going to learn if you took a small addressable market strategy. So
and just again, I think you like live in this, but for someone who hasn't had a genetic test, for a medical reason, what would be a scenario where you'd actually want that, and what would it do for you?
Yeah, so classically, diagnostics were not about genetics. They were about your cholesterol is high or some other hormone is low or whatever. Genetic diagnostics were first kind of proven in mass at breast cancer, where we know there are genetic predispositions that would change your treatment strategy, where the risk is high enough that if your mother or your sister or your grandmother, your aunt had breast cancer at age 70, people get cancer when they're old, but if it's at age 35, that's way scarier. And when we added genetic analysis on top of that, we could further partition that to, because they had this variant, they were early cancer patients. Mm-hmm. And then your doctor can help you make the best proactive decisions about how to avoid it. At the extreme level, that's like a proactive mastectomy. But there are lots of other intermediates, including like which type of drug would be most effective for you. Should you risk the downsides of chemo? Should you just wait? Right. So it worked with breast cancer. And then as we started being able to analyze more and more genes, we started discovering more and more things that it works for. I think one thing to keep in mind is that human geneticists, in general, they historically study like horrific things, right? Like whether you're studying fruit flies or mice or humans, like it's big effects. There's this old saying, like big mutations have big effects. Mm-hmm. Meaning, we study things that give you a heart attack at an early age or make you grow tumors or have crippling nervous system diseases, right? And there are lots of people at risk for that who don't know it.
Right.
But I think the real future is there's lots of genetic defect in everyone. We think the average healthy person has a couple of hundred genes with defective function in their genome. And there's probably lots of what we think of as subclinical symptoms wandering around across the whole population. So I think that's kind of the future vision of the company is everyone would benefit from having a full understanding of their genetic background. And it's a complicated problem that the doctors don't understand. The patients certainly don't understand. And they were really at the frontier of understanding. So that's a little bit of the history and a little bit of the future mission statement.
And so, I'd imagine that a lot of people listening to this have done one of the kind of consumer tests, like maybe like Ancestry or 23andMe. So how is what you do different from what happens there?
Yeah, I mean, it's a great question. And it's one that pre-COVID, riding on a plane, someone asks you what you do, and they're like, oh, like 23andMe. And you're like, oh, man, no.
Right.
So, I mean, the obvious difference to the like interaction with our customers is that historically it goes through a doctor. It's a medical test, and you want that provisioned and administered by a medical professional. And 23andMe is, it's a fascinating company, but they've focused on, things like whether or not you like cilantro, not whether or not you are at risk for a disease. And they have tried to move into a diagnostic space, but they're not built for that. And we finally acknowledged that a couple of years ago, after many years of not wanting to offer a medical diagnostic procedure directly to patients, because we didn't want people to go with information in hand, but not understanding an explanation that they could get from a medical caregiver. So that's the real difference is like we have medical caretakers in place, but we now have a strategy where we let patients initiate their orders. And that's really because there's a lot of the country that doesn't have access to one of the few thousand genetic counselors in the US. So there are places where it's a 6-month wait. There's places where like you're just not going to go. And thanks to telemedicine, thanks to software engineering, it's easier now for us to let a patient whose mother had breast cancer start the process themselves. We refer them to a telemedicine genetic counselor who helps them by being their medical caregiver without them having to wait 6 months to go to a medical center that's 100 miles away. And we think that's great. Does it lead to a little more confusion of like, well, we used to say we're not consumer facing, and now we have, patient facing order forms. But that's really the difference is like we are trying to help people with a complicated medical problem, not find out your ancestry, unless of course your ancestry has direct bearing on the medical risk.
Got it. That makes sense. And so, I mean, how does AI fit into this? Like you talk about a broad range. When I've talked to you in the past, I've been kind of shocked by the number of different ML kind of fields that you draw from. So I was thinking maybe you could give me an overview of the different problems where machine learning techniques can help with what you all are doing.
Yeah. So that we say AI, and it was an easy to adopt term, especially, for the last few years. But when I think of AI, I really think of like every chapter of a textbook of a field of computer science. It's been around for many decades. And a lot of it, thankfully, is machine learning, and some of it's not. So some of it is like optimization algorithms and robotic planning and so forth that has been around for a long time, and it's still making rapid advance in those fields, but maybe is a little less well known to machine learning folks. Mm-hmm. And then a bunch of it is, machine learning approximations that can make a problem tractable that wasn't tractable before. So, I mean, the actual applications, we have a key scaling problem in a lot of ways. We're like a manufacturing company, and that our volume tends to almost double every year. And we have a laboratory that has to run assays with, actual robots. We have rather complicated like standard operating procedures and business process models that need careful execution, not to mention like, audit logging and accounting stuff. It's the medical field, so you have to be compliant and follow, not just like HIPAA laws, which are complex, but also like contractual obligations to insurance companies and things like that. So there's a lot of complicated process modeling. And then there's a lot of knowledge worker problems, right? So we have on staff, dozens of PhD geneticists and biologists who have done this Herculean task of curating the medical genetic literature for any scrap of evidence that could inform whether this variant that seems to be breaking the function of a gene in a patient could actually be the causal factor that puts them at higher risk, because we still don't know most of the variants that are analyzed in medical genetics. We're still uncertain what their eventual effect would be. And that involves, literature mining, all the most contemporary NLP methods for entity extraction, relationship modeling, linking to ontologies. We don't get into things like summarization, because even the fanciest, most expensive model, it's not confident enough to write a medical report for someone, right? But the sort of language modeling that goes into something like GPT-3, like we can use that for concept embeddings, for extraction, for classification, for recommendation engines. So we have a lot of that NLP work that a lot of the rest of the world thinks of. Mm-hmm. And then I've got a fair chunk of computer vision problems, whether they're things like document processing computer vision or they're computational biology problems. And about half of my team is devoted to more core research, like advancing future products, doing academic collaborations with folks. So they're really trying to struggle with that problem I stated before, which is like geneticists traditionally focus on big diseases with big mutations, but there's a lot more subtle signal going on for almost everyone on the planet. And in a sense, it's a signal detection problem. Mm-hmm. And it's really a high order of complexity. If it's silly to think of it this way, but if you just imagine we have 25,000 genes working in combinations, right? How do you search a space of 25,000 combinations, 25,000 factorial combinations, right? So the hope is that things that were completely intractable before by enumeration could be tractable by approximation. Mm-hmm. And so that's, one of the great hopes for computational biology is that we can produce a search space with machine learning. And then, so we cover computational biology, knowledge, and operations. That's a big breadth of stuff to worry about. And then on top of that, I think there are things like graph embeddings for heterogeneous networks, where there's lots of reasons to believe that heterogeneous entities out in the literature shouldn't be just treated as like word tokens that you learn with a language model, but instead you can layer on causality and known relationships. Like biology is this kind of fascinating field, because if you really cared about Newtonian mechanics, then you probably don't need a neural network approximator to tell you like how fast the ball is going to roll down the inclined plane with a certain coefficient of friction and whatever, right? Because you can physically model it really accurately. Mm-hmm. And in biology, if you open a biology textbook, there are like all these cartoons of this protein binds to this protein and they both bind to the DNA and then the RNA is made and whatever. And they are like, they're not just cartoons that you memorize when you're a biology undergrad. They're like actual physical models of a material process of the universe. Mm-hmm. But the uncertainty is way higher, right? They are rough drafts. And because it's a tiny little, submicroscopic machines, right? We historically, like, we don't just take the picture. I guess that's less and less true because electron microscopy is now getting really good, and X-ray crystallography in some ways is really good at that. But for the most part, you do it by inference, right? You do some experiment and the readout is like, you look at a different colored of like jelly of agarose in a tray, right? And it's all by inference. So, when you see like one of those like CSI TV shows and they're looking at the big bands of DNA, that's a very abstract version of the actual physical process. And that's where like it's great for machine learning, because there's enough structure to that cartoon that you don't have to imagine every possible force vector. You have some constraints, but it's uncertain enough that it's not Newtonian mechanics. So modeling it with uncertainty and then using those indirect observations to guide your search, like in a lot of ways, it's a perfect field for using model-based machine learning.
Mm-hmm. Well, okay, so I'm taking like a mental note of all the different applications that you mentioned. I have so many questions on each one, but maybe we should start with the last one because it seems very intriguing, right? So like, why would a company like yours care about modeling like the chemistry of molecules? Like what does that do for you?
Yeah, so I mean, we know that if you put a change in this DNA sequence, that there's a high likelihood that it's going to change what amino acid is put in the protein. Like very, very predictably, we can predict that from basic molecular biology knowledge, but we don't necessarily know that's going to affect the function of the protein. Mm-hmm. And the easier ways historically to make computational estimates of that were, compare the sequence of that gene across 1,000 related species or, 10,000 humans and see like Is it always the same letter? Then it's probably important, because if it's not important, then evolution will let it float around. But there's actually quite a lot of flexibility in those proteins where they're still functional. So there might be a subset of people where it's different and it doesn't actually matter. And if you're an actual biochemist, then you might go do experiments in the laboratory, like seeing how the proteins actually touch each other and discovering that the enzyme works better or doesn't work as well. And it's really expensive and time consuming to do that at that like slow process and scale. But if you had molecular models of those physical properties, then you could do in silico experiments and say like, well, I can't be sure that the enzyme's not going to be as efficient, but based on a whole lot
say
of...
in silico, even like in silicon. I don't know. That's a new term to me, but I love it.
Yeah, right. So I mean, that's not me, right? That's a biology loves Latin.
That's great.
And yeah, so that's a well tested phrase in computational biology for a long time. But yeah, that's the right answer. That's what it means. So you're doing this simulation. And then you can say like, well, with some certainty based on the parameterization of those actual biochemical experiments that other people have done, this looks like a big change. And therefore it's going to affect the function of the gene. And therefore we have more reason to believe, in a very like Bayesian sense, like our belief increases that this is the cause of someone's disease.
And is this something that would be like kind of something you'd really do in the future, or is it like in use now? Is this like something that everyone would have to do to make a realistic model of like I guess how in use is this kind of modeling for deciding what genes to look at? This is something you do every day? Like,
I mean, this is definitely a thing that our company does. Like there's a team that does this. And, I think it's also an interesting example where I think it's a case where industrial research has more potential than traditional academic research just because of the volume, right? Like the biggest academic collaborations for genome sequencing don't actually get to the same number of people as come through our samples. And they're not as enriched for people who actually have disease. Like the big population genome sequencing centers in China and the UK and in the US, they're not generally systematically going after people with disease. Like we have an ascertainment bias. It's actually a benefit if we want to study disease, because people with disease and their families come through the door. And that means that we can do stuff that you can't do if you're working at the Broad Institute at MIT and Harvard, or at at Cambridge with the European Bioinformatics Institute. Like we have access to data that you can use these methods on that no one else can.
And how do you actually set up this problem? Like how do you like formulate it? I'm trying to like put this, my mind is just like, how would I set this up as like a machine learning problem that I could actually train on? Like is it standard, like what the loss function is, and like what can you actually observe to put into this?
Yeah, right. So, I mean, I don't think there's a canonically true answer to that question, but we can talk a little bit about the pros and cons of approaches, right? So, I mean, one thing is it's not like a consumer recommender system where you recommend products and people click on them and buy them, or they don't. In fact, like that's diagnostics in general has this problem of no ground truth. Like people die of symptoms on hospital beds, and their doctors don't actually know in some sort of like, Plato, Aristotle sort of way, like why they died. Right? It's just that we have a stronger belief about the causality. So you can take a labeled data set and say like these people were diagnosed and they had that variant, and I'll make a model that can predict that outcome with a supervised learning method. But you're not actually dealing with ground truth, because some of those people had the disease, they had the variant and they had the disease, but they actually had the disease because they smoked cigarettes for 50 years or because they were 90 years old or some other confounding factor was there, right? So if you want to try and think of it as belief, then you can go down the like Bayesian probabilistic graphical model, causality, Judea-Pearl, explainable AI path that I think people are excited about talking about. But you have to know like a lot of human knowledge goes into that. And it's not as simple as like, I have some labeled data and I'm going to train an arbitrarily deep neural network to approximate the softmax or something. So you end up working a lot with like, how do I take those physical models of what I think is going on in biology, and you try and design the algorithm to do that, whether it's with like causal graphical models, or it's just knowing like from these feature vectors, I can learn an auto-encoded representation that should, in theory, account for these factors we know from the physical model are important. And then I'm going to let the neural network set the weights by showing it what are observations that are the closest to ground truth that we'll ever have.
But it sounded like there's sort of sub problems here that people work on, right? Like you talked about, kind of people like looking at like proteins and mixing them together and kind of seeing what happens. Like, is that like a sub problem of this bigger problem where you could have different observations and build a different model around it?
Yeah, right. So, I mean, we do have a wet lab team that is like collecting basic molecular biology data. But one of the awesome things about biology is that lots of other people are doing that, right? So, lots of professors and lots of universities and lots of their grad students are collecting and publishing data in a way that is ingestible for us to learn some of those things. But there are places where you may identify a key deficiency in that knowledge set. You're like, well, it's worth it for us to do this experiment because it would really help us parameterize what we think is missing in this model. Mm-hmm. And so then you have like from an industrial research perspective, you kind of have to think about the cost benefit. Like, mm-hmm. Is it worth spinning up a wet lab initiative to do stuff that's hard to do at scale to fill in that? You want that feature vector. It better be worth it because it's not cheap.
Sure. Although it sounds actually kind of, well, I don't know, it's evocatively similar to like exploring a space of like hyperparameters for, for a...
I think maybe it's more like if you had a product recommender and you knew everything that everyone had ever clicked on, but it just still doesn't seem to have that much accuracy. So you send out some design researchers to talk to your customers and sit in their house with them and talk to them. And be
I see.
Like, oh, that's weird. Everyone's buying Adidas. I didn't notice that before. Is that in the model? Let's go find out all the shoes everyone buys and then see if that boosts the accuracy.
Got it. That makes sense.
But the thing is like if you had the whole life history of like me as an individual and everything I'd ever done, then you might be able to start down the path of that modeling. But that's crazy. No one would do that. You just look at my ad click data and make some recommender that if it has 38% accuracy is going to make a bunch of money for a ad company, right? But if you're talking about someone's health and like complex things like biology, then you want it to be higher accuracy, and you got to go actually model stuff out deeper.
So I guess another whole like field that you talked about doing is sort of the, what do you call it? Like sort of medical NLP or like, bioinformatics, right? And you talked about, I mean, this is one thing I've been kind of curious about. We've seen a lot of progress, very visible progress in NLP, like, notably like GPT-3, but also like these, word embeddings becoming super popular. Has that influenced bioinformatics? Is that like directly apply? Can you like fine tune these models on like medical text domains, or what's the state of the art there today?
Yeah, right. So, I mean, I think there's two big problems in the industry that people would love to solve. One of them is comprehending medical records, and the other one is comprehending the medical literature. Mm-hmm. And when you state the problems, they sound the same, right? It's like, I want to extract the entities, map their relationships, and then link them to ontologies so that I can structure the data and then make queries over it. And if you could do that, then, like the practical challenges are things like, can I show to one of our clinical scientists the right piece of literature at the right time to help them make the right insight about this genetic variant that's never been observed in someone before, right? And then if you look at the medical records, it's like, how do I take this like allegedly structured, unstructured data and turn it into something that's actually structured so that we can like make trajectories of people's disease progression or predict their risk. Mm-hmm. And so it turns out that training language models on like, Google Books and New York Times articles and Wikipedia does not actually help that much. Mm-hmm. But also kind of surprisingly, like several years ago, I did some experiments when I used to be at IBM Research, where I had a research group. We did some experiments where we had domain-specific corpuses and general corpuses. We would train the same models, and kind of to my surprise, the bigger general corpus helped more than the specific corpus. And that was like an early transfer learning kind of insight. Mm-hmm. Like, take the biggest corpus you can get and then transfer learn is a good idea. Mm-hmm. What's hard is the concepts are the same to humans, but when you look at a medical record, it says like MGM BRCA, and that means maternal grandmother had breast cancer. Mm-hmm. And you look in the medical literature that's published academically, it doesn't even talk about the relatives, and it doesn't even say breast cancer. It says, malignant neoplasm of the tissue. Like, you don't even know it's talking about the same thing, right? Mm. So mapping the concepts across is tricky. and just the syntax, right? Like the medical abbreviations, and it's almost like it's almost like it needs its own language model. So I mean, those are some of the hard problems for contemporary methods to actually work on, especially out of the box.
Mm-hmm.
But we do take things like, so we do take encoder decoder based sort of transformer models and adapt them pretty readily with supervised training. And it's definitely better than starting from scratch, but it still requires like, domain experts labeling stuff to get there. Or it takes, some like weak supervision data programming sort of methods where people are writing roles that make a lot of sense to weakly label the data. And, it's not as good as human labeled expert data, but that you can kind of bootstrap yourself into having a better data set to train on. So, some of those methods work really well in biology. Yeah, I don't know if that.
No, that's really interesting. Do you have the sense that, well, I don't know. I have the sense that recently NLP methods have improved a lot. Like when I look at, scores that I'm used to from like a decade or two ago, they just seem much better over the last couple of years. Has the same thing happened in the medical field?
Kind of, right? So like if you take like the scores on question answer data sets, like the model's better at answering Stanford question answer questions than I am, right? Super, very impressive, right? Like, but I don't think you would expect the same thing to be true with medical question answer and a bunch of like specialist doctors in whatever domain. So like no one expects a chatbot powered by a GPT-3 to be better at giving medical advice. But it doesn't mean, but that said, like the language model that's learned could be extremely useful for facilitating a human expert. And so I think that's where the hope is at this point. It's this kind of like AI assistant, better information retrieval, better support for the expert is the current hope, right?
Got it. And so I guess, like a general problem that a lot of people ask me about, and I know a lot of people listening to this kind of would kind of wonder about is how do you think about structuring your team? Like you talked about half the people doing kind of core research, but then also it seems like, what you're doing is very connected to what the company is doing. Like, do you try to like literally separate the people that are doing the sort of like applied stuff and research stuff, or do you separate it by the sort of field of work, or how do you think about that?
Yeah, it's a really good question. And I suspect the answer that I have today will be different than the answer I have in a few years, which I know is different from the answer I had a few years ago. And it feels like one of those things that like we'll keep reinventing. Like we'll keep reinventing, how to deploy software, and we'll keep reinventing how to provision infrastructure, and we'll come back to the same basic principles that people thought of a few decades ago, but we'll keep refining it. And so right now, like the company, the company was effectively, the company still worked like a startup with very clear product-driven vertical teams, and the idea that we were going to imbue a machine learning capability to the company is hard to figure that out, right? And it's a little different if you're at Google and like, well, the company is built on machine learning based information retrieval, so we kind of expect everyone to take a machine learning approach to something, right? So I guess the direct answer is like we have a team, we call it a functional team. Everyone goes to meetings together, hangs out together, checks in together, but people have different projects. And, it has definitely been hard for some of the team members. Like a common source of feedback is like, I don't know what everyone else is doing because everyone is working on something else. I'm used to working with 4 people on a specific project, and we talk every day in a stand-up meeting. And in this team, like everyone's doing something different. And so, for the people on the team who like went to grad school and experienced like what that's like to get a PhD, where it's ultimately up to you to do your thing, they're more comfortable with it because they're like, yeah, of course, we're all doing our own thing. In reality, like I really hope everyone's not doing their own thing, right? Like I hope that there is cross-fertilization and support, and it's like kind of inherently matrixed. But the goal is, we reserve some of the people's time for research, because if you don't explicitly kind of set aside the commitment, then it'll be absorbed by whatever like demand of the product team in the short term. And then we set aside some people's time to develop platforms that are modular and reusable, with the hopes that we continue to imbue that throughout the rest of the engineering teams. And then we set aside some people who are then like functionally assigned to specific engineering projects, whether it's to realize one of the research projects into production, or it's to leverage one of the platforms for a problem, or maybe it's just like someone has a pretty straightforward problem and they need like a scikit-learn model, and it's going to take someone like an afternoon to prototype it and 3 weeks to get it in production. So we stick someone in there for a sprint or two and make sure it happens.
I see.
Right? So I guess in some sense it's very zone defense kind of strategy. Like it has to be flexible.
Right. And do you then hire people who have sort of like knowledge of like multiple topics? These seem like such kind of deep fields that are kind of different. Like, is it possible to find someone that knows about multiple of these applications?
Yeah, so we hire people with specific expertise for sure. Like I am actually just extremely fortunate. Like I was a software engineer who went to get a graduate degree in computational biology at a time when doing that probably also meant that you're going to do wet lab biology. And then I went and worked at IBM in a research division with just this huge diversity of industrial interest. So I was exposed to lots of different AI methods. And that was not something that I knew was going to happen to me, but was really fortunate. And what that means is I met people in different industries at different conferences to understand like, oh, there's this kind of boutique thing that was, kind of popular 2 decades ago, but continues to be a core technology for NASA or Toyota. And not a lot of people pay attention to it, but man, it can solve a lot of problems, right? Which you're just not going to find like a Coursera course on. So, it's great because we can find people with that expertise. And if they're CS PhDs, kind of fortunately, right, so computer science PhDs are generally interested in stuff. Like if you practiced NLP algorithms, you're probably still interested in computer vision, right? So I think that's a fortunate thing, right? I can find someone with expertise in information retrieval, and they can still make really meaningful contributions to other types of problems and other subject domains. One of the harder things is getting the biology knowledge solid enough that they can talk to the biologist and the other stakeholders and quickly understand the problem statement.
That makes sense. And I guess like one of the things that you talk about a lot, I think, is the importance of engineering to making all this stuff work. Do you hire just like kind of pure engineers on your team, or do you rely on outside teams to provide that?
Yeah, no, I mean, I think it's really important. On the research projects, it's really important to be able to prototype things, because like I hope your listeners find me eloquent, but like my experience in life is I may have some beautiful complex system in my head and I have very little ability to communicate it to other people's brains, and building a prototype really helps. Totally. And you need a diversity of skills in even a small team to make that happen. Like it's just a waste of everyone's potential to ask the algorithms expert to write some React front end that you're going to throw away after you show it off to a stakeholder. Right. So it's better to have a JavaScript programmer on hand for that.
Do you have a ratio that you shoot for? I'm just kind of curious about this, of like sort of algorithms to like implementers.
I think it just depends, but we try to maintain like a bench of depth so that we can recombine it, right? Like I think a lot of really high impact projects can be done with like one algorithms person prototypes a thing, hands it off to 1 or 2 engineers who implement the thing, and then we further hand it off after it's implemented to an engineering team that's going to love and care for it in the long term, and maybe come back to us if they need new features. But to them, it looks like software that could have come from anywhere. Other projects you need, we have some of our more challenging algorithmic problems where we have we like the approach of probabilistic programming, and there's not a lot of mature frameworks out there for that. Like Google and Uber AI both popularized some, but you need some pretty heavy lifting on algorithm development, some kind of fearless back-end engineering chops to make anything happen. And then once you have the ability to make anything happen, then you also want to layer in like the computational biology expertise to make sure the right modeling step that I described before is happening. So, that could be a several person team just to make the prototype, because it's complicated and the tooling requires help, and it's not as simple as like a web backend and a React front end or something.
One of the things that I've kind of been noticing, we've at my company, we've seen more and more interest in customers coming in from pharma and kind of medical stuff. And it always feels to me like of all of our customers, it's the biggest kind of culture clash, like just like, basic stuff that I feel like I haven't discussed in a long time. Like, they'll be suspicious of like open source software. I'm just like, oh my God, like what?
Yeah.
Like, is it like, 1995, does that not happen at Invitae because it's sort of a newer company and sort of, more maybe CS focused, or do you also kind of feel that kind of working with biologists?
No, I don't think it's a problem here. And like, certainly I saw that problem with IBM customers at times. I was lucky, at IBM, they were huge investors in Linux 20 years ago. And like, it was clear to everyone why that continued to be the case. But I would see it from other companies who were like, I would prefer the lower performance, more expensive proprietary thing. Thank you. Right. I mean, I think, one of the virtues of Invitae is like, it does heavy on like a Bay Area ethos, and, get there faster, get there cheaper is a good idea.
Totally.
So I don't think there's any skepticism there, but, sometimes you collaborate with like the insurance agencies or the insurance payers or, like Medicare. And then you're into a whole ballpark of like, it's not even individual skepticism, right? It's like, and it's not even institutional skepticism. It's like codified in contracts, the skepticism, right?
Right.
Yeah. So, I mean, for us, it's not a problem at all. I think I would imagine, the bigger the company, the older the company. It's probably true in every sector, but a lot of the big old companies in technology got over it a long time ago.
Right. Yeah, that makes sense. Well, we always end with two questions, and I want to make sure we have time for them. They're kind of broad, and feel free to expound a little bit. But, one thing we always ask people is kind of when you look at like what people are seeing or what people are doing in ML, like what's a topic that you think people don't pay enough attention to? Maybe like a skill set that you'd like to hire for, but nobody's studying, or something that you'd like to spend more time on if you could.
Yeah. I mean, so just reasoning in general. Right? And I think this happens. If you go to like a general AI conference, whether it's one in recent favor like ICML or NeurIPS, or it's like the older triple AI sort of standard conferences, lots of keynote speakers will talk about like fast and slow AI or system 1 and system 2 or whatever. But I think like no one ever actually wants to do reasoning because it's so hard.
Right.
And but then you see like communities of self-flagellating academics lamenting that they're only competing to get a higher, F1 score on some published data set that's been around forever, and what's the actual use of it all. And I think this conversation is also often turned to like, well, if we were doing some more complex reasoning thing, then it would be more valuable for mankind. But it's just hard, right? So that's why I said earlier, like we're into the probabilistic programming ideas, because you can take a causal graphical model that can be highly explainable, and you can not have to Monte Carlo sample it until the end of time, like thanks to variational inference and frameworks like Edward and Pyro that make it a little easier. I think that's going to push our ability to reason about really complex things and bring human expertise in, and let people help correct the models and do a lot of the things that just frankly feel like people talk about doing, but are hard to do. And I think there's also a bias against systems in academic conferences, right? Like no one wants to write a quote unquote systems paper in a workshop. They want to write an algorithms paper that's going to get cited 10,000 times. But that work is probably more important. Right? Like putting together a thing that solves a problem is really valuable. And, I wish we trained grad students to think about that instead of to think about hyperparameter tuning effectively, right? And that's, if I could snap my fingers and change one thing about the field, I think that would be it, is like pay attention to complicated systems because they'll help you build things like reasoning engines.
It's sort of interesting. I guess I have not made a connection between reasoning engines and systems. Like those two both seem like kind of separate tracks. Is there something about like making working systems in your experience that really requires like reasoning?
Well, it's good. I mean, so, if you take an example like the word embeddings or graph embeddings, once you have that representation of similarity, you can rank documents and calculate a F1 score, but you can also give it to an expert and say, I found this thing for you. do you think it's the right thing or not? And if they say yes, you can further process it and extract some more information out of it for a specific purpose. And if they say no, then you could ask them, like, why not? And reason about the entities and relationships you extracted, and actually like auto refine your model from the feedback of the user. But that's like that's a HCI problem. That's a, you know, an interaction problem that you're not even going to start to touch unless you're open to the idea of like building some boring system that ties together a user interface and some backend systems that are not all machine learning, right?
Totally. Okay, so final question is basically, when you look at in your career kind of taking stuff from the sort of prototype version to like deployed in the real world and useful, where do you see the sort of biggest bottlenecks or biggest problems?
I think the biggest fundamental problem is when you work in industry and you have an existing company, but probably also when you have like a startup and you're trying to get funding for it, to have buy-in from the product philosophy from the outset, right? And to have some willingness that the prototypes might not work, right? So like you need a foundational, definitely going to work plan to make a product. But to have I'm going to reserve 20% of the resources to try this crazier thing. We'll prototype it, and if it works, it'll be great. You got to have the person who's going to take it to market care about that idea. When you have a bunch of researchers like hanging out, making cool prototypes, and then they take it around like a toddler who made a thing, and they're like, "Oh, look at this thing I made you! Don't you love me?" I mean, I think almost every researcher I've known in industry could identify with what I just said as the toddler. Because we all think we have some brilliant idea and we make a thing and we take it to people and they're like, I'm sorry, I have a deadline right now. I don't understand. Why does this thing that I already have a thing that recommends papers. I think it uses a regular expression, right? They don't care,
Right?
And they don't see the value. So, you know, you have to really get the buy-in at the beginning, or you can spend a lot of time making a hard thing and probably an expensive thing happen. And then it doesn't actually go anywhere. And it's more emotional than strategic. Like you have to like be open to the idea that they might not see the value in what you want to do. And that helps you prioritize what to do.
Interesting. We've not heard that answer yet, but that really resonates. That makes a lot of sense. Thank you so much. This is a lot of fun. I really appreciate your openness.
You're welcome. My pleasure.
Really appreciate it. Thanks for listening to another episode of Gradient Descent. Doing these interviews are a lot of fun, and it's especially fun for me when I can actually hear from the people that are listening to these episodes. So if you wouldn't mind leaving a comment and telling me what you think or starting a conversation, that would make me inspired to do more of these episodes. And also, if you wouldn't mind liking and subscribing, I'd appreciate that a lot.